they come. Martin. All right, guys, we're going to start chapter 22. This is going to cover respiration. Part of this will be respiration of various animals and how they get gas to exchange with their blood. And then we'll get into human respiration and human anatomy. Again, we're kind of shifting over more towards the human anatomy and away from the animal stuff the next few weeks. We'll finish our dissections today in lab. That should get us finished up with those. And we'll have our test over that coming up. And then we'll move into more human anatomy type stuff in there as well. All right. So we're a little bit out of sync with lab and lecture, but I think we're about to get caught back up. All right. Brad Robinson. All right. So again, we're going to look at, again, various forms of organs that will take air or oxygen out of the atmosphere and exchange CO2 with the atmosphere. So the whole goal is to get oxygen into the bloodstream to feed our cells, and then to get the CO2, the waste product, out. And that's really what gas exchange is. It's just moving those two gases in and out of the body. And again, different animals do this different ways. So we're going to look at things like the trachea type lung that's in insects and other arachnids. Other arthropods. And then we'll look at fish and gills and how gills work. And then we'll look at how the lung works. And then again, we'll get more into the human stuff. Lord. All right, so let's get started with this. If my clicker will work. For some reason, it's not wanting to. All right, I guess it's not going to work. Let me switch up real fast. I thought I could use my clicker. All right, so the mechanisms of gas exchange. How do we achieve this? How do we get oxygen out of the atmosphere and then CO2 out of the blood? Again, there's three different mechanisms we're going to look at as far as how insects get oxygen, and then how fish and other organisms get oxygen with a gill, and then we'll look at the evolution of the lung and how the lung became very efficient because the oxygen concentration is much higher in the atmosphere than it is in, let's say, water for a fish. So they have to have different mechanisms of getting this oxygen out of the air, or in the case of a fish, out of the water. So gas exchange is just the interchange of oxygen and CO2 between the organism and its environment. Again, we need oxygen for cellular respiration. This is something that had to evolve over time, because in early Earth, there was no oxygen until plants and other photosynthetic organisms started producing it. There was none in the atmosphere. So they had to be here first. And then as animals developed, they had to figure out a way to make oxygen non-toxic, because oxygen is one of those elements that wants to react with everything. All right. It forms free radicals. It forms all kinds of different compounds that are detrimental to life. So we had to figure out a way to lock that oxygen up. And organisms that carry out cellular respiration figure that out by putting it in the metabolic pathway. And that way you convert it over into less harmful material, so that you now actually have to have oxygen, even though it's toxic. There are still anaerobic bacteria that are around that oxygen is toxic to, and they can't live with it. So this is something that developed over time, the ability to get this oxygen out of the atmosphere. We also had to get rid of CO2, which is our waste product. All right. Now, in the body of a human or any other animal that carries out cellular respiration, they're carrying out basically a combustion reaction. You're taking glucose, and then you're converting that over into CO2 and energy. And basically, we have to get rid of that waste product that's a result. It's just like burning a piece of wood or gasoline. We have that CO2 come out of the tailpipe. It's the same thing with us. We're breathing out CO2 that's our waste product. The good thing is, though, plants utilize CO2. So whatever we breathe out, the plant takes in, and it's just a cycle. And the plant produces oxygen for us. So that's developed over time to where both are kind of dependent on one another for the different gases they need. But again, we need oxygen for cellular respiration, and then we need to get rid of the CO2. Right? So if we look at an alveoli of a typical lung, Basically, when we breathe in, the oxygen is going to diffuse into the blood, and then the CO2 is going to diffuse out of the blood. Now, it's a pretty um, simple mechanism, I guess you'd say, for oxygen. We basically diffuse most of that in, combine it with hemoglobin, and then it's carried throughout the body. CO2, on the other hand, though, is more complicated. It converts into ions that we use as buffers in our blood. So the bicarbonate ion is how most of the CO2 is carried in the blood, and then we have to chemically convert it back over into CO2 before we release it. And we'll talk more about that, and there's a big chemical equation I'll go over. I'm not going to get as in depth with you guys as I do in anatomy when I teach human anatomy, but I will get into a little bit of the chemistry just so you understand the difference between how oxygen is carried in the blood and CO2 is carried in the blood. All right, so there's three phases of gas exchange that occur in humans and other animals with lungs. First, it's breathing, just simply taking air in and allowing air to go out. And we'll look at that mechanism in a minute, how the lung is able to carry that out. Then we have to transport the gases by the circulatory system, and then we have to exchange those gases with the body cells. So the body tissues take up oxygen from the blood, and then they release CO2 from the blood. I should say from the blood, not to the blood. I don't know how that got in there, but so why can't humans survive for more than a few minutes without oxygen? It's basically part of our metabolic pathway now. We have to have it in order to carry out the combustion of glucose and get the energy from it. So without oxygen, we can't carry out that reaction. So it's required that we have it, and we have to have it in certain concentrations as well. We're going to look later at people that climb mountains like Mount Everest and how they are able to survive at those. And we're actually going to take a more in-depth look at the Sherpa people. They actually have a different physiology than most people on Earth because they are evolved to live in that high altitude environment. They've been there so long, their bodies have actually changed, and they're physiologically different than other humans. So we'll look at that in a minute and kind of see how that works, and how people that are non-Sherpa have to regulate their oxygen concentration with masks and pressurized oxygen and that type of thing. But we'll get to that in a few minutes. All right, so again, when we are hiking or doing whatever activity we're doing, we're breathing in oxygen, and then we're taking CO2 out of the blood and getting that out. That's the act of breathing, just taking the air in, pulling the oxygen from it, loading that air with CO2, and then breathing it out. The other is transport. We have to take it through the cardiovascular system to all the cells of the body in order for them to exchange oxygen. And that's where we get the oxygen into the mitochondria and CO2 out. Remember, the mitochondria is the powerhouse of the cell. That's where we make our energy, right? It's thought that this was once a free living bacteria and that it became incorporated in eukaryotic cells over time, and now it's part of the cell. And if we look at the mitochondria, it's very similar to a bacteria. It has a 70S ribosome instead of an 80S ribosome like we see in human cell, and it also has the ability to create its own ATP, and it has a membrane around it just like a bacteria would. So that's called the endosymbiont theory, that they were once free living and over time they became part of the cell because they can do things that bacteria do. And they are almost identical. They have their own circular DNA just like a bacteria cell. And so they're kind of different as far as the organelles go, but that's where we're going to exchange these gases, utilize that oxygen to make energy, and then give off that CO2 as our waste product. All right, so respiratory surfaces must be very thin. We have to have a thin membrane that has to be moist, and we need that for diffusion of oxygen and CO2. Some animals use their entire skin as a gas exchange organ. You know, we think of amphibians. They absorb a lot of the oxygen they get through their skin. Other animals, like an earthworm, get all of their oxygen through their skin, right? And that's why they have to live in a damp environment. So we'll look at different organisms and how they are able to get oxygen into their blood. And there's several different ways. In most animals, gills, a tracheal system, or lungs provide the large respiratory surfaces. But again, some animals use their skin for that, but they have to live in a damp environment. If an earthworm, for instance, crawls out on your sidewalk and it's a hot day, it's not going to make it very long. It'll end up drying up and dying. So it has to stay underground in that moist environment in order for it to carry out its gas exchange. All right, so here's an earthworm, and again, we're going to see the exchange of gases here. Our capillaries are near the surface of the skin, and then that is going to allow for gas exchange to occur. Again, things tend to diffuse pretty easily if you have a moist contact with the outside air. So oxygen, we're going to get into partial pressures later and how that works. But just realize the partial pressure of oxygen is a lot greater out here in the atmosphere than it is inside the animal, because the animal is constantly, uh, I won't say burning the oxygen up because that's not the right terminology, but it's utilizing that oxygen in that combustion reaction where we burn glucose. And through that, we're pulling the oxygen out of the blood, so it's consistently less as far as partial pressure goes inside the animal than outside. So that's going to drive diffusion. That's going to make oxygen want to go down its concentration gradient or pressure gradient in this case and diffuse into the blood. CO2, we're building it up in the body because we're utilizing that oxygen and glucose and making CO2. So its partial pressure is going to be higher inside the vessel than it is in the outside world. So it's going to want to diffuse out. So the earthworm has simplified that by just utilizing the skin and utilizing those partial pressure differences to allow that gas exchange to occur. All right. So blood's going to come in that's deoxygenated. It's going to release its CO2, and then it's going to come through and pick up oxygen and then oxygenate the blood and then go out throughout the earthworm's body. So that's pretty much a simple method of gas exchange. We just rely on the partial pressure differences with these gases to move them back and forth. Same thing happens with the gill, but now we're having to add water to the equation, all right? And we're also adding to the equation that we don't have a lot of oxygen available, all right? Oxygen is a resource in water that is very limited. In fact, if water temperatures get too high, the oxygen level goes so low that things can't live. I have a catfish pond at my house in Alabama, and it gets hot in the summertime, and it's fairly shallow, so it heats up, and the water temperatures can sometimes get up around 90, 92, 3 degrees, and that just gets to the point where there's not enough oxygen to keep my fish alive. So I have a big aerator out there that pushes the water up into the air, it cools the water, and it collects oxygen out of the atmosphere and brings it back into the pond. That's the only way they can really survive in some of these really hot spells that we have. Now, I don't leave it on all the time. I just leave it on when it's going to be very hot for a long period of time in the summertime. So fish have developed these gills with this huge surface area, and you can see how many little villi-shaped extensions it has on there, and that provides a tremendous amount of surface area to collect as much oxygen as possible from that water that's really a low oxygen environment. If you know anything about fishing, you know, certain fish live in certain areas. So if I want to go catch a trout, for instance, I have to go to the mountains. The reason being they have to have really cold water and high oxygen levels to survive. If a trout lives in water and it heats up, they're going to die very quickly. So mountain streams that are covered, you know, with tree line that keeps the water cool and keeps a lot of oxygen in there, moves through, you know, rapids and things that oxygenates it. Those fish can live there. And then if we look at something like a carp or a goldfish, which is a type of carp, they can live in fairly low oxygen environments. So they live in swamps and places like that where most other fish can't live. So again, it's a matter of how well they can get this oxygen out of the water. But it's the same principle here as far as getting oxygen in and CO2 out. We're relying on those partial pressures to make that difference, to push one in and one out. All right. Now we're also going to look at something called countercurrent exchange. And with fish, this is going to be very important because it allows them to fully saturate the blood in that low oxygen environment. And we'll get into that in a minute. Now, this is the tracheal system of an insect. So they don't have lungs, they don't have gills. Insects have little things called spiracles or openings on the sides, usually of their abdomen. And this allows air to come in and it just moves through their body. And this respiratory surface is going to spread throughout the animal's body, and it's going to allow it to absorb oxygen that way. So it's not a lung, it's not a gill, it's simply openings that allow oxygen and CO2 to exchange with the atmosphere. Right? So again, they have these little openings on the side, called spiracles that will allow this air to come in, and then that tracheal surface is highly branched, and that allows it to kind of diffuse into all the cells that surround it. And then we look at the lung, and the lung is going to be the same, or the same principle is going to be used with the lung, and that's to create the most surface area possible for gas exchange. So we have these little alveoli that are at the ends of the respiratory tree, and this will allow oxygen to move into the blood and CO2 to move out of the blood. So we bring CO2 and deoxygenated blood in, and the CO2 leaves the blood, and then that blood goes and picks up oxygen and then goes back into the circulatory system. And mammals have developed a really efficient way of getting oxygen with that four-chambered heart, where we have two sides. One goes to the pulmonary side, or the lung, and then the other is going to go to the systemic side, where we pump the oxygenated blood out to the body. So that's the most sophisticated way of exchanging oxygen with the environment. So the lung is kind of the best model that we see of doing that, or the most efficient way of doing that. All right, so when we look at gills, it's going to work differently than the other two in that water is involved. And that's the only place a fish can really get oxygen. Now, there are a few fish that can breathe air. They come to the surface and they actually gulp air into their swim bladder, and then they absorb oxygen that way. Those fish tend to live in really anoxic environments, or swamp-like areas where there's very little oxygen. So they have evolved to be able to even pull oxygen out of the atmosphere and start utilizing that, almost not quite like a lung, but similar to a lung, where they bring it in and then they're able to do that. Yes, betta fish are a great example of that. I'm glad you brought that up. I was trying to think of that fish. That's the one. That's why they can live in those little cups that you see in the pet store. They don't have to really change their water out very often, and they can breathe oxygen by gulping. All right. Carp do this, bowfin do this, some other fish that live in those swampy environments. But here, when we look at the actual true gill and how it works, we have to use this countercurrent exchange in order to saturate the blood. And what that means is water is moving past the gill in one direction, and blood is going to be moving in the opposite. And this allows them to fully saturate the blood with oxygen as it moves by. So we have this whole opportunity when we're touching each other here to absorb oxygen, so it can just keep getting more and more and more. So if I start absorbing here, I start pulling in more and more and more, because I've got fresh water coming by that's got what we say is 100% saturation, but it's a very low level of oxygen, but it's 100% saturation for the temperature of the water at that time. That's what that's getting at. So we bring in the most oxygen we can at this point, and then as that water moves, we can continue to bring in oxygen the whole way down. And what that does is it allows us to fully saturate the blood before it moves out to go to the body's cells. If we went the other direction, if they were flowing in the same direction, we would only get about 50% saturation, which wouldn't be enough for the survival of the organism. So this countercurrent exchange is developed so that we can fully saturate that blood. All right. So again, fish have adapted to do this, so they bring water in past the gill. If you've ever seen a fish, they sit and they'll open and close their mouth, and they're pulling water in by doing that. And that water then is oxygen rich, and it's going to pour over their capillary beds in the gill, and then it's going to pull out all of that oxygen, and then it's going to also exchange CO2 with the water, and CO2 then goes back out into the environment. Again, aquatic plants will utilize that CO2. And again, if you've got a good balanced pond or lake, you have enough aquatic organisms that are photosynthetic, like algae, to match what fish and other organisms that utilize that oxygen out of the water. So there's two ways you balance a pond. One is the ratio of bait fish to adult fish that feed on them, but also you need enough fertilization to get enough plant growth to supply the oxygen to them. And it's a really fine line to do that when you're making a man-made pond, for instance, because you have to set up the parameters and make sure that things stay that way. Or if you have a koi pond or something like that, you have to balance things out. Um, but again, these gills are very efficient at getting that oxygen because there's very little in the water. So they're constantly bringing fresh water through and then pulling that oxygen out of it. All right. So again, this is that countercurrent exchange mechanism. The water flows one direction, the blood flows the other, and you notice we are going to fully saturate that before it enters back into the circulatory system. So again, it's a pretty ingenious design. So notice that the percent oxygen is always greater in the water than in the gill, and that's going to allow for the movement down its concentration or pressure gradient. All right. And that's just showing you the same thing. So again, if the water moved in the opposite direction, you could only get about 50% saturation. By the time you got halfway down, that would be it. You wouldn't have any difference in the amount of oxygen in the water versus in the blood. You would basically balance out about halfway through. And once you balance out, there's no more exchange. You can't get any more oxygen in. All right. So notice here we have constantly more oxygen in the water than we do in the blood. So 15 to 5, 40 to 30, 70 to 60, 100 to 80. But if we were to run the other way, about halfway through, we would hit 50% here and 50% here, and then we couldn't bring any more in because we wouldn't have a gradient to go down. Right? So again, it's very important that they move this water in one direction and the blood in the other. Right. So there's two advantages to breathing air versus water. So if we look at the oxygen content, it's about 21% in the atmosphere. But if we look at water, it's only 0.001% oxygen. So again, those fish have to be really efficient at getting that oxygen out of the water. And being that there's so little oxygen, just a little bit of change in temperature can create a situation where the oxygen, the dissolved oxygen, is just too low for life to exist. And again, you see that a lot. In areas you'll get fish kills. There's one that's really famous down in Mobile, Alabama, in the Mobile Bay. There's certain times, and it only happens on a rare occasion. They call it the Jubilee because people used to go down, and when it happened, they could collect all the seafood and they had plenty to eat. But what happens is the oxygen level goes down so low in the bay, and it has to be the right conditions, where the weather conditions just right, the temperature's just right, and all the seafood starts to die and come washing ashore. Well, it's not dead yet, so it's not rotten, but they're dying from lack of oxygen. And people just go out and just grab tons of them, shrimp and crabs and all the sea life that's there, and fish and everything else. And that only happens when it's under the right conditions, and the water then has such low oxygen concentration, everything starts to die off. I wish I had a video of that. I should have shown that to you. I might bring it up here in a minute. Right. Now, the tracheal system of insects, this is going to have respiratory surfaces at the tips of tiny branching tubes inside the body. And this directly transports oxygen to body cells and moves CO2 away from them. And this greatly reduces water loss, right? So this is going to open with the spiracle on the side of the insect, and then it's just going to allow oxygen to go in and have direct contacts with cell. So we're not involving the circulatory system here. Right? We're just simply bringing oxygen in and allowing the cell to pull it out of the air and then put the CO2 in. So we don't have, blood circulating the respiratory gases. We just simply bring them into the body and bring them out. Much simpler than a lung. So here you can see our body cells, and these tips of the tracheole are going to provide the oxygen for these cells. So they basically just branch out to all of the cells. And notice here how much branching that occurs with these. So each branch goes to a cell to feed that cell. So again, this is much simpler than a lung or even a gill. And these spiracles on the side are where these openings occur to allow that gas exchange. So we have these openings all along the insect's body. Sorry, my throat's dry this morning. All right, so here you can see the openings on the caterpillar. And again, oxygen just going to go in and provide nourishment for these cells. So they're just going to open these openings. I don't know what happened to this diagram. I noticed this yesterday with this big green thing on it. But these openings for air just allow it to go into the body. and bathe these cells with oxygen, and then CO2 then will just kind of come back out of the cell and out of the spiracles. Very simple design here compared to the lung or the gill. Right, so in what ways does gas exchange in insects differ from that in both fishes and humans? The circulatory systems of insects not involved. It just basically allows the air to come in, bathe the tissues, and then come back out as CO2. So again, it's efficient enough to provide that insect with enough oxygen, but they don't have that circulatory system involved. All right, so the colonization of land by vertebrates was one of the pivotal milestones in history, and the evolution of legs from fins may be the obvious change in body design that helped this to occur. But the refinement of lung breathing was just as important. And if we look at, again, even amphibians of today, they still utilize their skin for a lot of their oxygen exchange because their lungs aren't very efficient. So they're still kind of almost like an ancient organism in the fact that they still have to absorb air through their skin. And that was probably the first way that these animals started getting oxygen, and then the lung developed later as they moved further and further inland. All right, so what we're going to do now is shift over to just a human respiratory system. So again, I'm not going to get as involved with this as I do in my anatomy class, but I will explain some things to you, and I'll tell you what you need to know for your test. And then some of the stuff I'm going to go over, I'll be like, I'm explaining this to you, but I'm not going to test you over this part. All right, but I think it helps just to show you some of the chemistry involved. All right, but again, I won't test you over the chemistry. That's a little more advanced than what this class is. So. All right, so the diaphragm is what separates the abdominal cavity from the thoracic cavity, and this is what helps ventilate the lungs. We inhale air through the nostrils into the nasal cavity. We filter that air with hairs and mucus surfaces, and then we warm and humidify the air. We sample it for odors, and then we allow that to move into the lung. So there's a lot that goes on before gas exchange actually occurs. So when we breathe in air to our nose, we have these nasal concha on the side, which are little ridges that stick out in the nasal cavity. And this provides a lot of surface area, but it also causes a lot of turbulence. When I breathe in, the air is going to kind of rotate around, and that gives it time to warm up and then gives it time to moisten so that when it gets into the lung, it doesn't damage the tissues. So they're very fragile tissues down in the alveoli. You've probably experienced this at some point. If you're out when it's really cold, and let's say maybe you're taking a jog or a run, or even if it's really, really cold, just walking out and breathing, you notice it hurts the lungs. Because you can't warm and moisten the air enough because it's so cold and so dry that when you breathe it in, it actually is painful. And you can feel that, especially if you're running in the wintertime. I remember when I used to play football and stuff, and we'd have to run in the late season, you could feel that burn in there. But again, it's just because that air is not being moistened and warmed enough before it goes down to those fragile tissues. Right, so inhaled air is then going to pass through the pharynx, the larynx, which is our vocal cords, the trachea, then the bronchi, and then the bronchioles, and then the alveoli. So all of this area that we're moving air through, we call this conductive zone. So the pharynx, the larynx, the trachea, the bronchi, and even to the bronchioles to some degree, we're not exchanging gas there at all. These are just conduits or pipes or tubes to get that air down to the alveoli. This is where all the action happens. All right. So the alveoli is where we're going to have that thin membrane, a lot of capillary beds, and that's where we get a lot of gas exchange to occur. All right. Now there's also something else that we have to produce, and that's called a surfactant. And that prevents the moist surfaces of the alveoli from sticking shut. It also helps to mix oxygen with the liquid or the blood by acting as a transition. Surfactant is, let me give you a definition of that and kind of an example. A surfactant helps two things that normally don't want to mix very well to mix very easily. Soap is a great example of a surfactant. So when I wash my hands with soap, what it's doing is allowing oil in my skin to mix with water so that I can wash away any dirt and stuff that's stuck to that oil. All right. So when I wash my hands, think about if you wash your hands a lot, they typically get really dry. It's because you're taking all the oil out of the skin. right? So a surfactant is going to help two things that don't want to mix easier. In this case, it's going to help oxygen mix with the fluids in the lung so that we can get that diffusion into the blood. All right. Now, mucus and cilia in the respiratory passages protect the lungs, and that allows us to catch bacteria and pathogens like viruses and things before they get down into the lung. Remember, we're exposing ourselves to the outside world by breathing in. We need a mechanism to keep those pathogens and things from trying to get into our body. So we're going to see a lot of what we call lymphatic tissue around the lung, around the intestinal tract, where we're in contact with the outside world. And in those lymphatics, and you may not be aware what the lymphatic system is, but in those lymphatics, we have those lymph nodes you may have heard of, but we have immune cells there. And those immune cells are scanning everything to make sure nothing gets through. But this is our first line of defense, the mucus and the cilia. Hopefully we'll trap, let's say, a bacteria, for instance, and then we'll cough that mucus up into our throat, we'll swallow it, or we'll spit it out, and then that bacteria is gone. If we do swallow it, our stomach acid kills it. All right. The cilia are little hair-like projections in the trachea, and that helps to pull that mucus up and get anything out of the lung that may have gotten in, whether it be dirt, pathogens, anything else. If you smoke, then those cilia become paralyzed, and that's one reason smokers have a chronic cough, is because they're not able to get that stuff out of their lung, and on top of that, they're putting bad stuff into the lung with the smoke itself. So they're not only getting the bad stuff from the smoke, but they're getting bad stuff from the environment in there that they can't get back out as well. All right, so how does the structure of alveoli match their function? Well, they're thin, they're moist epithelial tissue, and that just allows dissolved oxygen and CO2 to easily diffuse in and out of the capillaries, right? This also gives them a huge amount of surface area, and we'll look at alveoli in a minute. They're little round sacs, and there's bunches of them, and they're kind of in a bundle, and it just provides a tremendous amount of surface area for us to exchange these gases. All right, so this is an alveolar sac, and these are individual alveoli. Notice the capillary beds that surround them, but we have billions of these in our lungs, and that creates a tremendous amount of surface area for us to exchange these gases. All right, so if we look at your lung down here, these are going to be found at the ends of these smallest terminal bronchioles that you see here. So we're going to breathe air in, come down the trachea, and then it's going to simply get divided off into smaller and smaller and smaller. And it usually divides about 23 times before we reach the alveolar sac. And then once it gets there, that's where the gas exchange is actually going to occur. All right. So again, this bronchiole is just a tube to get it there. All right. And so are the trachea and the main bronchi. These are called conduits, or the conducting zone. That's just where we're bringing air in. We're not exchanging gases. It's not until we get down here that that occurs. All right, so evidence accumulated from thousands of studies have shown that smoking causes lung cancer and other respiratory diseases. The good thing is, I have noticed this, I guess, probably more so in the last 10 years than I have before. I've been teaching 20 something years now, but I have noticed the incidence of smoking went way, way down. In fact, my anatomy class, we're doing the respiratory system right now. And I have 24 people in there. I mean, we were doing experiments with spirometry where you measure the lung compliance and all that. And I always ask, does anybody smoke? Because I like to compare them to someone that doesn't, so we can see if there's a difference in the lung capacities. And yesterday, or not yesterday, it was last week, when I asked, not one single person smoked. Now, there may be somebody in there that didn't want to admit it. But in the past, I would have 5, 6, 7 that smoked. So the incidence went way down. People have kind of started to take notice that, this is a deadly habit that you don't need to do. And if you do smoke, it's a good idea to quit. I used to smoke when I was younger, and I quit 96, somewhere around there. My girlfriend made me quit. I won't tell you how she motivated me, but I quit. But it was not easy to do. It's a highly addictive substance, nicotine. But once you do, in about 8 years, your lung will be almost back to where it was before if you haven't done any damage. Now, that's not to say you can't form cancer cells. It only takes one cigarette to initiate a cancer cell. Now, hopefully, your body gets rid of it by your immune system coming in and wiping it out. But the more you smoke, the longer you smoke, the more likelihood you're going to get lung cancer. Now, this is a um, chart of the death rate, and you notice we see a trend of lung cancer going up and up and up until about 1970. Now you think, well, man, most people smoked back in the 1920s, and they did, but the odds were they probably died of something else before lung cancer got them. And that's one reason we see this trend. Life expectancy goes up, and the older you get and the longer you smoke, the more likely you are to get cancer. The other thing, too, is we start seeing the manufacture of cigarettes rather than people rolling their own. So back here in the 20s, people were rolling their own cigarettes. They would buy tobacco and then roll it themselves. That made them smoke less because it was expensive, number one. And number two, they had to roll their own cigarettes. They wouldn't smoke as many. So when commercial cigarettes started coming out, that's when we started seeing a big uptick too, because now it was easy access. People could smoke more. And the more cigarettes you smoke, the more likely you are to get cancer. So there's a lot of factors that play into this. But we're starting to see this actually level off and even go down to some degree. I wish I had the data from 1970 until now. Again, the incidence of smoking, people smoke a lot less today than they used to. All right, now this I'm going to try and speed up if I can, but this is going to show your body after 30 packs of cigarettes. And what they have done is just basically set up a model with cotton balls, and this is basically going to represent your lung. Um, but this takes a while to go through, so I may speed it up part of the way through if I'm able to, just to get it to run through, because it's just kind of repetitive. And I'm gonna cut this off so it doesn't feed back. So I'll turn it back on when this is over.
Well, if you smoke, I hope this gives you the incentive to quit. And I wish you luck in your.
All right, so that just gives you an idea of just 1 month of smoking, what you're putting in your body. Again, your body is going to remove a lot of that material, and you'll be able to get rid of it. But over time, that is going to accumulate. And again, there's a lot of carcinogens in cigarette smoke. So if we look down here, you can just see some of the different things that are in cigarettes. So everything from insecticides to ammonia to solvents like toluene, hexamine, candle wax, cadmium from batteries, butane from the lighter fluid to light a cigarette, methane, arsenic. So just a lot of different things that are in there, and a lot of these are known to cause cancer. And we now know there's enough data out there to show cigarette smoking is the leading cause of lung cancer. The second leading cause of lung cancer, though, is radon. And that's a gas that we have here in Georgia, and it's a major problem, especially where I'm at in Waco, kind of northward of here and west of here into Alabama. The bedrock contains a lot of uranium, and it breaks down through radioactive decay into radon gas, which is radioactive, and it seeps up in your house. If you have a big crawl space or a basement, it'll build up there and then seep up through the floor, and you're breathing that in all the time. It's odorless, it's colorless, you don't know it's there. So if you live in one of these radon prone areas, you can go by Home Depot or order one online, a radon detector, to see if you've got a high level in your house. And if you do, then come put a barrier down in your basement to prevent that gas from coming up. Again, that's number 2 behind smoking, is the leading cause of lung cancer. Now, e-cigarettes are not really any better than smoking. Well, you would think it would be, since it's just vapor, but we're starting to see a lot of long-term effects from this as well, not only on the lung, but on the developing brains of teenagers. These things are marketed in a way, in fact, they've just started passing laws to make some of the flavored stuff illegal, because they're afraid, all these nice candy flavored, vapes, that people are going to get addicted very young, and it's really tempting for young people. So really, this is not much safer, if any safer, than regular cigarettes. And there's a new condition called popcorn lung that they've associated with vaping. It's caused by the vapor that comes into the lung, and it causes the alveoli to expand and burst like popcorn. And that's becoming a major issue too. But again, nicotine's highly addictive, no matter what form it's in. If you do smoke cigarettes and you switch to a vape, it's probably a little bit better for you, but it's still better to quit altogether. But if that's a stepping stone to take, that's fine. But the whole goal should be to quit, not just to convert over. Right. All right, so this is going to get through vaping, and
this is an.
Sorry, every time I turn my mic off, it cuts me off. So I'm going to cut my mic, and then I'll turn.
This is an X-ray of a patient's lungs. And here's an X-ray of those same lungs just 5 days later. See all that light gray? That's fluid, which filled their lungs because of a life-threatening lung disease, linked to vaping. For years, vaping has been touted as a safer alternative to smoking cigarettes. But now, some vaping products are killing people. So what's going on? And is it really bad for you? Vaping typically refers to inhaling an aerosol, which contains either nicotine, in the case of e-cigarettes, or some form of cannabis, such as the psychoactive chemical THC. And in the last few years, it has exploded in popularity, especially among teens. I mean, just look at this graph. It shows the percent of high school students who use e-cigarettes. In 2018, it was over 20%. And that's what makes this news so scary.
A patient died from a severe respiratory illness, and it could be the country's first vaping-related death.
That was in August of 2019. And by early September, the number of reported deaths linked to vaping had climbed to at least 6. Not to mention, there were at least 450 possible lung injuries tied to both THC and nicotine vape pens.
I have been saying this from the beginning. Looks like it's becoming an epidemic.
That's Dr. Melody Prasada, who's treated at least 2 patients with what she calls vaping-associated lung injury.
So over here, we are seeing our 18-year-old patient who, when he first presented to the emergency room with chest pain, fever, coughing, and vomiting. And as you see over here, it is the black is for the lungs, and you see nice still black.
But 5 days later, his lungs were filled with fluid because of inflammation, which she said was linked to vaping THC.
Once you come to this point, the chance of dying can be as high as 70%.
So what's causing all that inflammation, all of these lung injuries? The short answer is, we don't really know. Doctors say it's likely not the nicotine or THC itself, but rather other chemicals inside the liquid which get vaporized when you inhale. One possible culprit is vitamin E acetate, which health officials have found inside many vape pens that have been linked to the recent string of lung injuries.
When you start inhaling oils, any type of oil, vitamin E is an oil. Any type of oil, if you start to inhale to your lungs, you are going to create problem inside your alveoli.
Alveoli are small bubbles inside your lungs that transfer oxygen to your blood. And she says that vitamin E could interfere with the lining that surrounds them called pulmonary surfactant. But according to Dr. Mikhail Kazachkov,
I don't think vitamin E is the only guilty, substance here.
Because when it comes to vape pens,
You're going to inhale dozens of other substances, which are not necessarily advertised, but they're there. There is definitely needs to be a carrier, a vehicle, because nicotine cannot be delivered just in a pure form.
until researchers find out what's behind vaping-associated lung injuries, the CDC says don't vape. But here's the thing. Lung injuries, they're actually not the only risk associated with vaping. One small study, for example, found that kids who used e-cigarettes might be exposed to higher levels of nicotine than those who used traditional cigarettes.
It would not be unusual to have extraordinary high concentration of nicotine in vape.
And
Nicotine is not benign.
it raises your blood pressure, which can increase the risk of having a heart attack. And if you're a teen,
It is known to cause problems with the brain development.
not to mention, it's highly addictive. Now you might be thinking, well, isn't vaping still better for you than smoking? But the answer isn't so simple. You see, smoking is really bad. It kills more than 480,000 Americans each year. And vaporizers, they typically contain fewer toxic chemicals than the 7,000 or so found in cigarettes. But at least in the short term,
There is absolutely no reason to say that vaping is healthier than smoking. In my opinion, vaping is worse because we are scared. We don't know what to do.
so if nothing else, there's probably a better alternative to smoking than vaping. And if you're not already a smoker, you definitely should not start vaping now.
It is at this point very clear that vaping is not only unhealthy, but it is very dangerous. This is not anymore a debate. This is a proven fact that vaping is killing people.
All right, so that just gives you an overview of smoking and vaping. Again, some of these videos are a little bit dated. That one's probably 5 years old or better, or close, maybe not 5, it might be 3 years old. Anyway, again, the studies are still out there, whether vaping is safer or not. Again, if you don't smoke already, you shouldn't vape to begin with, just so you don't get started with nicotine. But again, it's very addictive. All right, what we're going to look at now is Boyle's Law and a little bit of math involved with it to explain how we breathe. Most people don't have any idea of how we actually bring in air and release air. And you're going to see this too when we get to the Everest video of why people can't breathe at the top of the mountain, right? But breathing is ventilation of the lungs through alternate inhaling and exhaling, all right? And we use what's called negative pressure breathing, all right? So this is going to be a result of us changing the volume of the chest cavity. And that's where Boyle's Law comes in. And the Boyle's Law states that pressure 1 times volume 1 equals pressure 2 times volume 2. So if we change the volume, we change the pressure. So if I increase the volume, I decrease the pressure. It's an inversely proportional relationship. So what happens to breathe is that we take our diaphragm and we pull down on it, and it makes the chest cavity bigger. When we make the chest cavity bigger, that lowers the pressure inside, and then we have pressure out here that's much higher than the lung, and that forces air to go in. Everything always moves from high pressure to low pressure, right? Think of a hurricane. It's a very low pressure environment, and all the winds are getting sucked into it because it's higher pressure outside of the hurricane than inside. And that's where all the intense wind comes from. Right. So we do the same thing. We make our chest cavity bigger, we lower the pressure inside, and then all that high pressure air wants to rush in. Right. Now that's an active process where we have to burn ATP in order to cause that muscle to contract. All right. So our diaphragm contracts down, we make the chest cavity bigger, pressure gets slower, we breathe in. To breathe out, we just simply relax. And that's a passive process. All we do is relax the diaphragm, and the stretchiness of the muscle and the elasticity of it causes it to push back up and make the chest cavity smaller. When we make the chest cavity smaller in volume, then that makes the pressure go up. And now the pressure inside the lung is higher than outside, and that causes air to move out. So low pressure inside, air moves in, high pressure inside, air moves out. Right? And it's all due to the diaphragm, and to a lesser degree, our intercostal muscles that cause that chest cavity to expand and get bigger. So that's how we actually breathe. All right. So again, Boyle's law, I'm not going to make you do the math with this. I do in my anatomy class, but it's pretty simple math. If I say, okay, I have a pressure here that's, let's say 10 ATM, I'm just throwing some numbers out there to make it easy. So 10 ATM, and let's say we have a volume of 10 liters, right? So 10 times 10 is 100, all right? Now, what this says, if I change any of these other values, pressure or volume, the other is going to change. So let's say I go from having 10 liters as my volume to 5 liters as my volume. Now what's going to happen to my pressure? Well, if I take 10 times 10, that's 100, and divide by 5, that goes to 20, all right? So my pressure is going to go down, or up, excuse me, it's going to double, all right? So I decrease my volume by half, and then the pressure is going to go up by double. It's an inverse relationship. As one goes up, the other goes down, all right? And as one goes down, the other goes up. So again, that's kind of the math behind this to explain how us making our chest cavity bigger and smaller causes the pressures to change. All right, so again, inhalation, the diaphragm contracts downward. That makes the cavity bigger, and then that causes air to move in. When I relax the diaphragm, it pushes back up, and then that's going to cause the pressure to increase in the lung, and that's going to push the air out. Now, this is fine and dandy if we're at sea level, all right, where we have a nice 1 atmosphere of pressure. It's easy for us to overcome that and make our pressure lower in the lung. It's really easy to do, all right? But what happens when we go up in elevation is there's less air above us, so the air pressure is much, much less. Think about, it's the same principle like when you dive into water. The deeper you go, the more water you have on top of you pushing down on you, and the pressure increases. And you can go down even in a lake and your ears start to pop, or even in a pool that's really deep. So the same thing happens with the air. When we're at sea level, we have all this air above us. And even though we can't see air, it has mass, just like anything else. So all of that air is pushing down on us from the top of the atmosphere all the way down. But when I go up 30,000 feet, like where a plane flies or the top of Mount Everest, now I only have just a teeny bit of air on top of me. So the pressure is really low. And being that the pressure is really low, the molecules spread out and it makes the air really thin. So there's not as much oxygen available to me. So both of those factors play in. But literally, if I go to the top of Mount Everest and I try to breathe, it's hard to get the air to come in because I can't make the pressure low enough in my lung to be lower than the pressure outside because it's already very low. All right. And even if I can do that and get some air in, there's not as much oxygen in it, and I'm still not going to get enough to adequately serve all of my cells. So when you go to Mount Everest to go hike to the top, if you're not a Sherpa, you have to go up and take oxygen with you and pressurize it in a canister so that you can actually physically breathe. It kind of pushes it into your lungs. All right. And people die all the time on Mount Everest. And the bad thing is when you die up there, you don't come down. They leave you there. In fact, there's trails that have markers. Hey, Fred died over here. There's Fred. We need to turn left there. They just leave your body up there and it freezes and it just stays there. And they don't bring you down because it's so difficult to do that they would risk people's lives getting you off the mountain. So people die up there all the time. And thousands of people a year go up there. In fact, so many are going now, they've actually polluted the place with all of their waste. You got to remember when they poop or whatever, it stays on the mountain. And then if any of that ice ever melts, all that poop comes downhill with it, and it gets into the streams and stuff down below. And now they're having a big problem with pollution from all the human waste that's up there. Right. So why is inhalation an active process, whereas exhalation is passive? Because we have to contract the muscles to bring in air to make that chest cavity enlarge. Right. Exhalation, you just relax the muscle and it doesn't require any energy. All right. So this is a fairly long video, but it's really interesting. And we're going to look at the physiology of Sherpa versus everyone else and why they can go to the summit of the mountain without any oxygen, without any need to take anything with them. In fact, they are the guides that take people up, and that's their job, is to take people up the mountain. But they have lived at such high altitudes for so many thousands of years that their bodies have actually changed to accommodate living there. All right. This isn't acclimation just like we think of when we go to the mountains. You know, if you go live up in the mountains of Denver, Colorado, so let's say you're a mile high, your body's going to change and you're going to start making more red blood cells as a result of being up at that elevation because the oxygen level is different. But when you come back down, you change back and you start producing less red blood cells at that point. But a Sherpa, they're always this way, and their bodies don't change. And even if they live at low altitude, they still have the same abilities that they do when they're at high altitude. So it's not an acclimation. This is a genetic thing where they have developed this over many, many years. So again, I'll let him go through this. It's a really interesting video.
People from different parts.
Hold on, I gotta cut this off again. Keep forgetting every time I feedback on here.
People from different parts of the world have different genetic characteristics. That's fairly obvious. An easy one to spot is, of course, skin color, but as the name suggests, this is only skin deep and a poor way to determine genetic difference. For example, there's more genetic diversity in the continent of Africa than the entire rest of the world. And since this video is about superpowers, I'm not sure that skin color really confers any, unless, of course, you count being more resistant to sunburn or less likely to be stopped by the police. Yet we do have real-life X-Men living amongst us. Not literally amongst us, unless you live on the roof of the world. The Sherpa are an ethnic group originally from Tibet and now residing in Nepal, and they are the greatest climbers in the world. No, not that kind of climbing. I mean that they can climb higher and perform better at high altitude than any other humans on the planet.
Everybody says, I climbed Everest. Wrong. It is Sherpas who climb. Okay. It is Sherpas who take us to the Everest.
Sherpas are honestly the greatest human beings on the planet.
To understand some of the concepts, we're going to need a crash course in altitude medicine. At sea level, atmospheric pressure is 1 atmosphere. At 5,500 meters, it's half an atmosphere. And at the summit of Mount Everest, it's less than a third. The proportion of air around you that's made up of oxygen is the same, 21%, but there's just less of it. There's less of everything. The air is thinner. The body struggles to survive in an environment it was never evolved to experience, unless, of course, you are a Sherpa. Now, don't get this confused with acclimatization. That's the essential process that mountaineers have to go through before they ascend the high summits. Remember, we talked about hematocrit in a previous video. That's the amount of red cells and hence hemoglobin in your blood. Now, cyclists may boost this with drugs, but you can do it naturally just by existing at altitude, as your body attempts to deal with the low oxygen levels by increasing the oxygen carrying capability of your blood. You also start to hyperventilate, breathe faster. This blows off carbon dioxide. Carbon dioxide is acidic, so your blood starts becoming alkalotic or more alkaline. Your kidneys then have to try to compensate and correct your pH. This sounds okay so far, right? Well, we need to talk about hypoxic pulmonary vasoconstriction, or HPV. Hypoxia from the Greek, hypo meaning low and oxia meaning oxygen. Let's say you've got a damaged part of your lung. Low oxygen is detected and blood vessels contract to try to divert blood to healthy bits of lung instead. There's no point supplying dead lung with blood. But at altitude, your lungs detect low oxygen everywhere, even if your lungs are completely healthy. The blood vessels contract all over, reducing gas exchange, making the whole situation worse. In a process we don't really fully understand, changes in blood vessels cause fluid to leak out into your lungs and around your brain. These two complications are called high-altitude pulmonary edema and high-altitude cerebral edema, and they require urgent descent because they can kill. Sadly, any boost in your hemoglobin is temporary. After I came down from altitude, I returned to being a sea-level sucker in a matter of weeks. Even if I had stayed at altitude my entire life, my son would have still been born with the physiology of a lowlander, even though, as you can see, he is a natural-born mountaineer. Yet, even if a Sherpa is born and raised in Holland, their kids will still be born with adaptations making them better suited to altitude than their Dutch school friends, even if the highest they've ever climbed is the top of a windmill. So this is genetic. Let's get to the good bit. What actually are these mutant superpowers that I'm raving about? Tales of Sherpa resilience abound. They've been found on the mountainside, semi-conscious with oxygen saturations below 40, and survived. Most of the Everest records, including summits without oxygen, are held by Sherpas. Every foreign climber will have experienced some degree of mountain sickness, a thumping headache, blurred vision, nausea and weakness, only to look up and witness a Sherpa bouncing past them carrying 40-kilogram loads as if they were on a Sunday stroll. Their internal mechanics, from the cellular level to the size of their lungs, are tuned like a Le Mans supercar.
It's like having Michael Jordan or LeBron James like serving you like cereal in bed while you're still in your sleeping bag. Because these guys, they really are some of the best athletes in the world, and they're spooning this dude's sugar.
Sherpas produce 30% more power than lowlanders at altitude. They have more capillaries per square centimeter of muscle than lowland climbers. They have bigger chests, greater lung capacity, as well as higher measures of all lung physiology, like peak flow. Remember HPV? It just isn't seen in the same way in Sherpa. Like mountain goats or yaks that live at altitude, Sherpa lungs just don't seem to misinterpret hypoxia and precipitate the same counterproductive tightening of the blood vessels. A lowlander's heart and major blood vessels start remodeling, i.e. changing function and shape, both in the short term and long term at altitude. But Sherpa hearts don't show these adverse changes. Lowlander cardiopulmonary dynamics change dramatically as they ascend from sea level to altitude and start to acclimatize, whereas Sherpa physiology remains remarkably similar at all levels. They are far, far less likely to develop altitude sickness, with fewer heart and breathing problems and better sleep at altitude. Lowlander basal metabolic rate increases at altitude, which is why so many climbers lose weight. But Sherpa metabolic rate is unaffected, and weight loss is not reported, with some even putting on weight with all the high energy food you eat on a climb. They have high levels of nitric oxide, which keeps blood vessels open and avoids high altitude pulmonary and cerebral edema. They have better blood flow to their brain above 8,000 meters, reassuringly known as the death zone. And pregnant Sherpa don't experience the same complications of pregnancy. They have healthier babies and lower infant mortality. The crazy thing is, they don't have that thick, ragu-like blood with a high hematocrit. In fact, their hemoglobin is lower than a lowlander's. Mitochondria, you've no doubt heard referred to as the power stations generating energy inside cells. They're actually found in lower concentrations in Sherpa than in lowlanders. So this doesn't make any sense. They've got lower levels of hemoglobin and lower concentrations of mitochondria. How are they doing so much better than everyone else? Because the answer isn't in increasing oxygen delivery, it's in actually changing the way oxygen is used. And this is something that takes thousands of years to select out. Sherpa muscles, both the heart and skeletal muscles, prioritize the use of carbohydrates over fats. You've no doubt heard the hype surrounding zero-carb ketogenic diets, so you might know that muscles get their energy from two main sources, sugars and fats. In most people, fat is preferentially used in fasting states and has lots of energy, but the process of burning it requires more oxygen than burning carbohydrates. In fact, per oxygen molecule, adenosine triphosphate yield is 25 to 50% higher using glucose as a substrate rather than fat. Therefore, by preferentially using sugars, the Sherpa muscles just need far less oxygen. And what's more, their mitochondria are more efficient. Us lowland dweebs have got the equivalent of a two-stroke engine, whereas Sherpas are running high-tech hybrids. Phosphocreatine can be used as an energy supply when ATP is scarce, and lowlander levels of phosphocreatine go down as we ascend. But Sherpa levels actually increase. Researchers stated that it was almost as if they became healthier as they ascended to the altitudes for which they were evolved. There's much we still don't understand, and only a handful of genes have been identified, but there are probably many, many more that contribute. In 2014, a team from UC Berkeley published the fascinating finding that a gene responsible for the high-altitude adaptation of hemoglobin amongst the Sherpas, an EPAS1 variant nicknamed the super athlete gene, came wholesale from the Denisovans. The Denisovans were a subspecies of human rather like the Neanderthals. And just like Neanderthals, our ancestors bred with the Denisovans. The Han Chinese also inherited the EPAS1 variant, but as they didn't live at altitude, there was no advantage to having the gene, and hence it was lost. But the Sherpa kept it going. There are other high-altitude communities in Ethiopia and the Andes, but the Himalayan plateau has been continually inhabited for about 30,000 years. What I love about these findings is that the doctors and scientists that undertook this work have demonstrated as clear as day evolution that's taken place in fairly recent history. Much of the information in this video is from research published by the Extreme Everest team based at UCL, who have done extensive work in the field and used data from high altitude to help everyday patients with hypoxia in intensive care. The avalanche of 2014 and earthquake in 2015 were two horrendous tragedies for the region, claiming the lives of many Sherpa along with thousands more Nepalese. They shone a much-needed light on the often exploitative conditions under which many Nepalese work, and the risks they endure to provide for their families by taking wealthy Westerners to the summit. Nepal is a breathtakingly beautiful country with the warmest people I've ever met. Please do check out some of the links below. Don't forget to let me know what you thought of the video. I'll end with some Star Wars trivia.
Right, so that just gives you an idea of some of the different physiology that Sherpa have versus people that live at lower altitudes. It makes them more or makes them more acclimated to that environment. Now, breathing is automatically controlled. We have control centers in the brain, which is going to respond mainly to CO2. Most people would think, if I ask you, which gas is the one that's the most important as far as regulation of breathing, most people would say, well, oxygen. We got to get oxygen. But it's really the CO2 that triggers breathing. In fact, if you've ever known someone that's either diabetic or has lung issues, they go through ketoacidosis as a diabetic, or they may go through metabolic acidosis if they have a lung issue like emphysema or something like that. But CO2 will build up in the blood, and then CO2 converts over to carbonic acid that then gives off a hydrogen ion and causes the pH to drop. And that pH drop triggers them to start breathing heavily. So if you know someone that's diabetic and you start seeing them panting, that's a sign they're going into ketoacidosis. Ketones are organic acids that they produce as a diabetic, and those ketones will drop the pH as well. So they'll start breathing, trying to get rid of CO2. And if I can get rid of CO2, that brings my pH back up again, right? So again, it's not really oxygen that plays a big role, but CO2. And CO2 is, like Stephen said, very deadly because it can kill you when you go into acidosis. My grandmother had COPD and emphysema, and she used to have to go to the hospital all the time because her CO2 levels would go up. And it almost killed her a couple of times. She finally passed away from something else. But with patients that have those issues, lung issues, or even diabetics, it can be deadly. So this is something the body really monitors, is those CO2 levels. All right, so how's the increased need for oxygen during exercise accommodated by the breathing control centers? Again, as we're exercising, our body is working more, making more CO2, and therefore our body is going to be triggered to start breathing heavily. So again, even when we're exercising, it's not really the need for oxygen that triggers us to breathe fast. It's the amount of CO2 building up in our blood. All right, but by doing that, we inherently get more oxygen because we're breathing in more. Now, one of my diagrams, I don't know what happened to it. It had that green line you saw earlier, but anyway, it just showed number 1 and then went to 2. So this is just the second step. But our normal blood pH is about 7.4, so a little bit on the basic side. And then the blood pH falls due to rising levels of CO2, and then that's going to increase our heart rate, and it's also going to increase our breathing rate. Right. So this is going to signal the brain to send a signal to the lung to start breathing more heavily or increase the depth of ventilation. And by doing that, we get rid of our CO2 level, CO2, and then that level falls, and then our pH rises back to normal again. So this is kind of a negative feedback system. But again, if it's being caused by something other than just exercising, like the lung is damaged, or again, ketoacidosis and diabetics, then that's going to cause the same trigger, but we may not be able to get back to normal. And that's the problem, because we don't have the ability to get enough oxygen and CO2 transported in and out of the blood because the lung is damaged, or we're providing acids from other sources like ketones. All right. So again, this is a natural thing for us to do. We start to exercise, we get CO2 buildup. Again, we start pumping the heart faster, our brain sends signal to the lung to breathe faster, and that gets us back to normal. And really, in a healthy person, surprisingly, our blood pH really never changes that much. It's only if you have lung damage that you can't get back to this point. So once we start exercising, our blood still stays around 7.4 because we're breathing faster, getting rid of more CO2, right? But it's that trigger initially of CO2 going up that tells us to start breathing faster. Right, so now we've looked at getting oxygen into the bloodstream and CO2 out. Now we need to transport it, and we do this with our circulatory system. Right, so the heart pumps oxygen-poor blood to the lung, where it picks up oxygen and drops off the CO2 waste product. And then the oxygen-rich blood returns to the heart, and then it's pumped to the body cells where it drops off oxygen and picks up CO2. So we have two circuits with the circulatory system. We have what's called the pulmonary circuit, which is the right side of our heart. That's going to pump blood to the lung, and that's going to get oxygenated and come back to the left side of the heart. And then that's going to be pumped through the systemic circuit that goes to the rest of the body. Now, we do have a 4-chambered heart. So when blood comes into the heart, it goes into the atria, and then the atria then has a valve between it and the ventricle, and then the blood moves into the ventricle, and the ventricle is actually what pumps the blood out. So again, each side of the heart has its own job. The right side pumps to the lung. The left side is going to pump to the rest of the body. And we dissect a heart. In fact, we may get one out and look at it. I got a big bull heart that's about that big. And we'll look at it. The left side is much, much thicker than the right side, because the right side only has to pump to the lung. So it doesn't need as much muscle to do that. But to pump through the rest of the body, the left side is going to be a lot thicker. And that's an easy way to tell which side of the heart you're looking at when you dissect one. So these are our circuits here. So again, the right side here is going to pump blood out. So we'll start with the ventricle down here. So the ventricle pumps out. We go to the lung. We dump off CO2. We pick up oxygen. That then comes back through the left atria into the left ventricle. And that pumps out to the systemic circuit. We deliver oxygen to our cells. CO2 then enters the blood. And then we come back through the right atria. And then the right ventricle pumps that again to get more oxygen. And again, this is a circuit. So almost every minute, your entire blood supply is moved through the heart, right? So every ounce of blood every minute moves through your heart, and that heart works constantly. So we need to make sure we take care of our heart and make sure it's working properly, because it needs to be very efficient at doing this, and it does this all the time, 24/7, your whole life. So again, we need this to be healthy and pumping correctly. If our heart fails to pump enough blood to provide our tissues with enough oxygen, we call that heart failure. And we can have left side or right side heart failure, and fluid will build up in certain areas. So if I have left side heart failure, fluid's going to build up in my lung. If I have right side heart failure, fluid's going to build up in my extremities, like my legs and arms. And we'll talk more about that when we get to circulation later and get into the heart and start looking at that stuff. All right, so let's look at what gases are in the atmosphere and what percentages. All right, so the air is a mixture of gases, and as such, it's going to exert pressure, but it exerts pressure in a weird way. You look at the total air pressure, but you have to look at individual partial pressures of each gas that's in the atmosphere to determine how much of it's there and how much of it we're going to be able to utilize. All right. So each gas has a partial pressure, and there's literally thousands of gases in the air you breathe. All right. But most are in very, very small amounts. All right. But the two big ones are nitrogen at about 78% and then oxygen at about 21%. All right. And it's the oxygen we carry about. Nitrogen, we don't really care about because it doesn't do anything. We breathe it in, we breathe it out. The only time you worry about nitrogen is if you're diving and you're under high pressure, let's say in the ocean. You can't come up too fast, or nitrogen bubbles will form in your blood, and that's called the bends or decompression sickness, and it can be fatal. But typically, breathing, like we're out here, we don't worry about nitrogen. All right, even though there's a lot of it, we don't utilize it. We utilize the oxygen in the atmosphere. So when we look at partial pressure, we're going to look at how much oxygen's partial pressure is in the atmosphere. Again, we say it's 21%, but it's going to exert a fairly high partial pressure compared to what's inside of us. Now, this is going to kind of go over this. There's several of these little mini movies in a row to explain this, but this will go through partial pressure and kind of show you how gases move in and out. If I can get it to work. Let me cut my mic and then we'll come back.
Let's start by looking at the movement of respiratory gases between blood and the body's tissue cells. Oxygen molecules are unloaded from hemoglobin, a protein in red blood cells. Oxygen diffuses into the blood plasma, through the capillary wall, into the interstitial fluid, and into cells, where it is used in cellular respiration. As carbon dioxide is produced by cellular respiration in the cells, it diffuses into the interstitial fluid, through the capillary wall, and into the blood plasma. Some CO2 remains dissolved in the plasma, but most enters red blood cells. Some CO2 combines with hemoglobin. Most of the carbon dioxide, however, reacts with water to form carbonic acid, H2CO3. Carbonic acid breaks up to form a hydrogen ion, H+, and a bicarbonate ion, HCO3-. Hemoglobin picks up most of the hydrogen ions, preventing them from making the blood too acidic. The bicarbonate ions diffuse out of the red blood cell into the plasma. Oxygen-poor blood carrying carbon dioxide leaves the tissue capillaries and moves through blood vessels to the heart, where it is pumped to the alveolar capillaries of the lungs. When blood gets to the lungs, hemoglobin gives up its carbon dioxide and hydrogen ions. Bicarbonate combines with hydrogen ions to form carbonic acid, which is then converted back into carbon dioxide and water. Carbon dioxide diffuses out of the cell, out of the blood plasma, and into an alveolus in the lungs, where it is expelled with exhaled air. Meanwhile, oxygen from inhaled air diffuses out of the alveolus, into the blood plasma, and into the red blood cell, where it combines with hemoglobin. Oxygen-rich blood then leaves the alveolar capillaries and travels to the heart, where it is pumped through blood vessels to tissue capillaries. There, red blood cells deliver oxygen to tissue cells. As carbon dioxide is produced by cellular respiration in the cells, it diffuses into the interstitial fluid, through the capillary wall, and into the blood plasma. Some CO2 remains dissolved in the plasma, but most enters red blood cells. Some CO2 combines with hemoglobin. Most of the carbon dioxide, however, reacts with water to form carbonic acid, H2CO3. Carbonic acid breaks up to form a hydrogen ion, H+, and a bicarbonate ion, HCO3-. Hemoglobin picks up most of the hydrogen ions, preventing them from making the blood too acidic. The bicarbonate ions diffuse out of the red blood cell into the plasma.
Now, I wanted to show that again because this is a very important reaction. Again, CO2 is hardly any of it's carried as CO2. A little bit's going to be dissolved in the plasma like we saw here, and a very small amount is going to produce what's called carboaminohemoglobin. And that's going to connect with the amine group on hemoglobin and attach there. But that's very little. The vast majority is going to be carried as this bicarbonate ion. Now, this acts as what we call a buffer. and a buffer prevents pH changes. All right. So if there are any hydrogen ions, now notice these are locked up here, so they're not going to contribute to the pH of the blood. But let's say we do have some hydrogen ions that are being formed from some other acid source. It's going to combine with bicarbonate and then be neutralized. And that prevents our blood pH from going out of control. So that's why we call this a buffer. And this is our major buffer in our blood. But this is also the major way that CO2 is carried. All right. All right. So I don't know why that repeated the second time, but it is important to understand how that works. Okay. Camera. Whoop. There we go. So most animals transport oxygen bound to respiratory pigments, and we call these hemoglobin in humans. This is going to contain iron, and if you don't get enough iron in your diet, then you become anemic because your body can't carry oxygen efficiently. Now, anemia is a kind of a catch-all term. There's many forms of anemia. You can have pernicious anemia, sickle cell anemia, iron deficiency anemia. Anemia is a word that just means you can't carry oxygen efficiently. All right. So again, this hemoglobin is going to pick up our oxygen as long as we have iron available. Now, most people don't have a problem with iron, but some females do, especially because of the menstrual cycle. You lose a lot with the blood there. But most men typically don't have a big problem with it. But if you do have low iron, there's ways to get it in your diet. Green leafy vegetables like spinach and things are really high in iron, but also cook with an iron skillet. You will actually get some iron in your food because it comes out of the skillet into your food. If you've ever eaten out of an iron skillet, you almost taste that little bit of metallic taste to it. Like if you cook an egg in an iron skillet, it tastes different than if you cook it in like a nonstick pan because you are getting some of that iron. But it's very important that we get that iron for our hemoglobin to work efficiently. So it's used by almost all vertebrates and many invertebrates to carry oxygen. So that's kind of a universal theme between living things. And it transports oxygen and a little bit of CO2, and it also works as a minor buffer as well. So this is our hemoglobin. So notice we have 4 heme groups that are here, and this molecule itself can attach to 4 oxygen atoms. All right, so we can carry 4 on each hemoglobin. Now, each time this hemoglobin moves through the system and goes by our cells, it's usually only going to lose 1 of those oxygen. All right, this gives us a lot of carrying capacity or excess capacity for oxygen. So if I dump off 1 oxygen, I still have 3 left, even when it goes back to the heart to be recirculated to the lung to pick up another oxygen again. So we usually lose 1 and then add 1. Start exercising, then we may lose 2, or if we're really exercising, we may lose 3. But that just gives us that buffer, that extra amount of oxygen that we can go above and beyond what we normally need by carrying that on here. So again, normally at rest, we'll get rid of 1 oxygen from this heme group. For exercising, we may lose 2. For really heavily exercising, like running a marathon, we may lose 3. But you usually never will lose that 4th one. All right. Hemoglobin has more affinity for oxygen when it has oxygen bound to the other heme group. So if I have only 1 oxygen here, it's really hard to remove that. It's easy to remove the first one. It's a little bit harder to remove the second one, even more difficult for the third one, and almost impossible for the 4th one. Now, if we think about this, when we have our oxygen saturated here with 4 and we carry it to the cells, the person's only going to lose 1, all right? So let's say that person stops breathing for whatever reason, all right? The reason you do CPR is to keep that blood moving through the body. They may not be breathing, adding oxygen to this hemoglobin, but they still have those 3 on there. So if you're doing CPR and doing chest compression, you're moving that blood to the brain, and that brain can still get some oxygen from that hemoglobin because it still has those 3 bound to it. So your job with CPR is not to save the person's life. It's just to keep them alive until help gets there by keeping the brain alive, keeping oxygen flowing to the brain. So they don't even recommend doing breaths anymore with CPR. It's really compression only. All right. And all you're trying to do is get that blood moving through the body so they can get some of that excess oxygen off of this molecule. Now, fetal hemoglobin attracts oxygen more strongly than the adult hemoglobin does, and this enhances the oxygen transfer from maternal blood or the mother's blood in the placenta. And then at birth, rising CO2 in fetal blood stimulates the breathing control center to make the baby start wanting to breathe. So when they're born, that CO2 builds up, and then all of a sudden they want to take that first breath. All right. Again, when animals are born, they do the same thing. But again, we need to look at partial pressures here. This is what drives this to move oxygen into the blood. And again, along with the greater affinity for oxygen, the baby will receive oxygen from the mother's blood that way. All right. All right, so that gets us through the respiratory system. Again, these are some of the questions to read over for your test to make sure that you have the information you need to do that. There's also some diagrams. So for your next test, I want you to make sure you know all the parts of the respiratory system. So this is a good diagram to practice with. You might want to print this out, fill it in. There's one in your book that you can go by to do that. But make sure you know this. We'll put that on your test. All right. Now let me look and double check at something here. I don't know when I had your next test slated. I want to make sure. Tell you right. All right, what's today? The 18th. All right, your next test is going to be due on the 24th, which is coming up very quickly. All right. I'm going to have to change some things. We're running a good bit behind on here. Let's move this out one more week. And that way I can get done with some of this other stuff. I'm going to start circulation here in a minute. I'll move test 3. I'll put an announcement out for you to let you know for sure when that test date will be. Let me see how far I get with this stuff today. I've got about 30 more minutes. I want to make sure everything is on there. So 20 through 25. So all we have to get through is circulation and the immune system. And I can do that probably next week and finish up. So we'll just put it off one more week, and I'll try to catch back up on the backside of this. This class just has so much material that it's hard to keep up with everything and get it all in by the end of the semester. So I'm going to go ahead and pick up with the circulatory so we don't get behind. So give me just a minute. Let me see if I can pull that up here. All right, so again, I'll put out an announcement about the new test date. Do the 31st. That sounds like the right day. Let me double check my calendar here. I think Halloween, yeah, it'll be the 31st. Be Halloween day. Now I will open it up before then. That way you'll have an opportunity to do it over the weekend. I know some of you may have Halloween plans and stuff, but I'll open it up so you'll have several days to get that done, Madison. All right, so we've already started kind of talking about circulation because the respiratory system and the circulatory system are pretty much intertwined with each other. You know, we breathe in, get oxygen in the lung, the oxygen then goes into the blood, and then we utilize the circulatory system to move it around the body. Now, the heart is the pump that drives the circulation of blood. And then blood flows through a closed circuit of vessels to every tissue in the body. Now that delivers oxygen from the lungs, and then again, it's going to pick up waste for disposal. Now there's more than just CO2 that's waste. We have nitrogenous waste also that need to go to the kidney to be removed. All right. So we need to remove that CO2, but we also have those other metabolic wastes that we need to get rid of. All right. Now this is the first artificial heart I want to say the guy that received this lived for a couple of months. I may be wrong on the time period, but it wasn't very long, but he lived long enough to show that this technology could work, and it's been improved a lot since then, right? But again, this was the first one that was developed to mimic the 4 chambers of our heart. All right, so circulatory systems, we're going to look at different animals. The main thing we're going to focus on is the chambers in the heart. How many chambers does a fish have, for instance, or an amphibian or a reptile? You're going to see this is going to change as we move up the ladder from a single chamber, basically, all the way up to our 4 chamber that we find in mammals, right? We're also going to look at structure and function of blood vessels, and then also the structure and function of the blood itself. All right, so gastrovascular cavities function in digestion and transport. In an open circulatory system, the heart pumps fluid through open-end vessels that bathe the tissues directly. So we have both an open system and what's called a closed circulatory system. So an open system, like we see in insects, basically the heart pumps and then it just basically delivers the blood out and it just flows through the cells, but it doesn't have vessels that return it back to the heart. Right? So an open system, the heart pumps fluid through open-ended vessel, and then they just bathe the tissues directly. In a closed system, we move through what's called a capillary bed, and then that's where gas exchange is going to occur, but the blood stays inside, or at least most of it, and goes back to the heart. Now, what we're not seeing with this, especially with our system, is the lymphatic system, and it's going to pick up the fluid that leaks out of the capillary bed and return that back to the circulatory system so it can be pumped again, right? So these are 2 major types of circulation, the open system and the closed system, right? So here you see our heart, and basically you have open vessels, and they will just leak out, and that will be pumped again, but we don't have vessels returning that, right? Now, if we look at a fish, we have a heart with 2 chambers. We just have a simple atrium and a ventricle, all right? In some of the lower animals, we only have 1 chamber, and it's basically just 1 vessel that pumps, like in an earthworm. It really isn't a true heart. It's just simply a vessel that pumps, all right? So it does have that same movement, but it doesn't have all the chambers that we see in a regular heart. So in a fish, we'll have an atrium and a ventricle. So we have a receiving chamber and a pumping chamber, all right? And again, we're going to move this 2 chamber to a 3 chamber and then to a 4 chamber heart, all right? And then we pump out of the heart into the large arteries, and this branches into arterioles and then into capillary beds. So if we look at our fish heart, again, we have an atrium and a ventricle, so blood, and this is a closed system. Blood is going to go from the atrium into the ventricle, is going to be pumped out to the gills. The gills are going to pick up the oxygen, or not pick up the oxygen, the blood is going to pick up the oxygen from the gill, and then that's going to circulate through the body and then come back into the atria again and then back to the ventricle. So again, this is a closed system with a 2-chambered heart. So what are the key differences between an open system and a closed system? Vessels in an open system do not form an enclosed circuit from the heart through the body and then back to the heart. And the circulatory fluid is not distinct from interstitial fluid. So it's not really even truly what we think of as blood. It's just a fluid that just kind of rotates around through the body, all right? So if we go back to this, we just simply have a heart that will pump the fluid that's in the body, and it just circulates the fluid around and around. Remember, we have those spiracles that allow air to come into those trachea, and then that can pick up the oxygen. So we don't have a true lung in the closed circulatory system where we can bring the blood back. And that's kind of the major difference. There's no lung here to provide oxygen. So we're simply oxygenating all this fluid, and then we're just simply pumping it around the body, right? So that's an open system versus our closed system where we take the blood and move it around. A fish 2-chambered heart pumps blood in a single circulation. So again, we don't have that double circulation like we see in a human. You know, we have a 4-chambered heart, we have a systemic circuit, and then we have a pulmonary circuit where we have 2 different distinct blood flows. All right. Within a fish, we only have a, where did fish go? Here. All right. So again, we don't have a special part of the heart that goes to the gill. We just simply move it through the gill and back around, through the gill and back around. So again, we see that with the 4-chambered heart, we're going to have a separate system to the lung and a separate system to the body. Okay, so land vertebrates have double circulation where we have that pulmonary and systemic circuit. Amphibians and reptiles have 3-chambered hearts, and then birds and mammals have that 4-chambered heart. All right, they still have the double circulation even though they have 3 chambers. It's going to work a little differently than the 4-chambered heart. All right, so again, our fish, we simply just move it through the gills, through the system, back through the gills, through the system. So we have 1 circulation instead of 2. And then if we look at a frog, it's going to have the double system like we have, right? So we pump out to the lung, it's going to come back in, and we're going to pump back out to here, and then we're going to come back into the heart. So instead of 4 chambers, this one only has 3. So we don't have an atria on this side. We just simply return the blood to the ventricle, and then it pumps it out, all right? So again, you can kind of see the progression from a fish to an amphibian to a mammal. Right? So if we see a mammal, again, we have 4-chambered heart, but we still have that double circulation. All right? Systemic circuit, pulmonary circuit. All right, so what's the difference between the single circulation of a fish and the double of a land vertebrate? In fish, the blood just goes in one direction. All right, it goes from the heart to the gill to the systemic, heart, gill, systemic. Whereas in the 3 and 4-chambered heart, we go to the lung, back to the heart, to the systemic, out to the lung, back to the heart, and then the systemic. So it's a double circulation. All right, so let's look at human. Second, I got to check this. I get an insurance deal going on. Okay. All right, so we're going to look at the human cardiovascular system and the heart. Again, we have a 4-chambered heart, and again, we have kind of the most efficient heart there is as far as organisms go. So blood flows through the double circulatory system of humans. Blood comes in through the superior or the inferior vena cava. The superior is going to drain down from the top of the body. The inferior is going to bring the blood from the bottom of the body. All right, and then these are going to go into the right atria, and then that's going to move out of the pulmonary artery, and then that's going to return through the pulmonary vein, and then it leaves through the aorta to go to the systemic circuit. Now, one important thing to remember with circulation is that we usually think of arteries as being vessels that carry oxygenated blood, and that veins are carrying deoxygenated blood. But with the pulmonary circuit, it's just the opposite. All right. So when we move out of the pulmonary artery, it's deoxygenated. It goes to the lung, receives oxygen, and then it comes back in through the pulmonary vein as oxygenated blood. All right. So the true definition of an artery is something that leaves the heart, and the true definition of a vein is something that enters the heart. So kind of keep that straight. It doesn't really matter if it's oxygenated or deoxygenated. But we typically think of the arteries as oxygenated because in the systemic circuit they are. But in that pulmonary circuit, they're just the opposite. So make sure you keep that in mind. All right. So pulmonary circuit, again, is in yellow here. And then in green, we see the systemic circuit. So notice we go to the lung from the right side of the heart, and then we come back to the left side of the heart to go out through the systemic circuit. So again, we're going to have that double circulation where we take it to the lung and then take it to the system. Now, I want you to know this for your test because I'm going to ask you to trace the blood flow. So what you need to do is just start at one point, and it can be arbitrarily anywhere, but we'll start here with the right ventricle. So the right ventricle is going to take blood to the lung. That blood then is going to come back into the left atria. That's then going to go into the left ventricle, and then that's going to go out the aorta. That goes out through the systemic circuit on both ways, down below and up top to the brain. And then that brain blood is going to come back through the superior vena cava, and then the systemic blood from the bottom of the body is going to come back through the inferior vena cava. So it's just a circulatory pattern that goes out and back in again. So again, just make sure you know this diagram. I'm going to ask you probably on the test, take the blood flow from this part of the heart back to this part of the heart. All right. So again, just make sure you really know this chart pretty well. It's not that difficult. All right, so why does blood in the pulmonary veins have more oxygen than the blood in the vena cava? Because the pulmonary veins carry blood from the lungs where it picks up oxygen. Remember, it's just the opposite. The pulmonary veins carrying oxygenated blood, whereas the pulmonary artery carries oxygenated, right? The vena cava is returning blood after delivering oxygen to all the tissues of the body. All right, so this is just going to take you through the blood flow in mammals, and we are a mammal, so this is mimicking what our blood does. Let me cut my mic first.
In mammals, blood pumped by the right side of the heart passes through the lungs and enters the left side of the heart. This is the pulmonary circuit. Blood pumped by the left side of the heart is distributed to the other body organs and returns to the right side of the heart. This is the systemic circuit. This pattern, called double circulation, ensures vigorous blood flow to the organs because the heart pumps the blood a second time after it returns from the lungs.
All right, so that just gives you another representation of the blood flow and how it moves through the body. Now, I've heard these words pronounced wrong. It's actually diastole and systole. I've heard diastole and systole. I've even heard doctors say that before, but technically it's diastole and systole. All right. So diastole and systole is the correct way to pronounce it. But this is the cardiac cycle where blood flows from the brain, from the veins into the heart chamber. And then systole is where contractions of the atria push blood into the ventricles, and then stronger contraction of the ventricles push blood into the large arteries. Now we'll look at the EKG in a minute, and I'll explain what's going on with each phase. But I'm not going to get that in depth with it like I do with my anatomy students. Now the heart valves are going to prevent backflow of blood. I call these check valves because they act like a check valve that you use in plumbing. For instance, I have a well on my property in Alabama that's 350 feet down in the ground, and my pump is a submersible pump all the way at the bottom. So when I pump water up and I cut the water off, or I cut the pump off, I don't want all that water coming back down 350 feet to have to be pumped again. All right. So I put in a check valve, and what that check valve does, water can move past it this way, but it can't come back down to the pump. So once it leaves the pump and goes through that check valve, it's going to stay up into the piping so that it doesn't have to be repumped again. And that's the same thing that happens with our heart. We have these valves that prevent backflow. So once it leaves an atria, for instance, and goes into a ventricle, when the ventricle contracts, I don't want it going back into the atria. That's what's called an incompetent valve if it does that. And that's called a prolapse when it goes backwards. And so we don't want those valves doing that. We want them to lock in place and prevent that backflow. All right. So the volume of blood that can be pumped from each ventricle is called the cardiac output. All right. And again, that's going to be determined by how strong the heart is and also whether those valves are working correctly. All right. So my cardiac output will go down if my valve doesn't work properly and some of that blood goes back into the atria. That's less blood that's going to go out of the aorta, for instance, all right, to the bloodstream. So we really need those valves to work, and I'll show you some diagrams of those in a minute. And then heart rate is going to be the number of heartbeats per minute. Now, cardiac output, we have a formula for that. We take basically the amount of blood that can be ejected times the heart rate is going to tell us the cardiac output. All right. So again, that's how we calculate that. All right. So if we look at our typical heart, And again, I want you to know this too for your test, this diagram. So make sure you make a note of that. But what happens when we have blood, and let's say that's coming back from the lung and it goes into the left atria, and then it goes into the ventricle. We want this valve, this AV valve, to close off, all right? And this is basically going to close off so that we can push all of the blood out of the aorta instead of it going back up into the atria. So we want this as a one-way deal here, right? So this is going to be our AV valve. Now, on the left side, that's called a mitral valve. And then on the right side, it's going to be called a tricuspid valve, right? So this is going to, again, prevent backflow so we don't get blood moving back into a chamber we don't want it in. So once the blood passes, we want it to go out of the aorta. Now, you don't see really much of it, but this semilunar valve here, the aortic semilunar valve, is going to do the same thing. So once we push blood out into the aorta, we don't want it coming back into the heart. So that's going to act as a check valve there as well. We also have one on the other side, all right? So again, when we pump the ventricle, this valve is going to close. We're going to push blood out of the pulmonary artery, and then that's going to go out to the lungs. We don't want it coming back in. So this other semilunar valve, the pulmonary semilunar valve, is going to prevent backflow here. All right. So again, make sure you know this diagram where all these valves are located. And notice the thickness of the heart. Like I told you earlier, the left side is going to be a lot thicker. Notice the thickness here versus here, because I have to pump a lot more blood to the systemic circuit than I do to the lung, or at least not more blood, but a longer distance. Let's put it that way. All right. So the heart is relaxed during diastole, and then the semilunar valves are closed. All right. And then during systole, we open the valve by pushing that blood out. And again, that's going to prevent backflow from coming in. So these valves are going to open and close in one direction. All right. So that when blood goes past, it doesn't come back in again. Now, the SA node is our pacemaker. All right. And this is going to set the rate of contractions. Now, it doesn't set the rate completely. We have a little bit of a delay at the AV node, and that's going to slow the heart rate down just a little bit. And what that does is it allows time for the ventricle to fill before it contracts. All right. So we have a brief delay, a couple milliseconds, and then that slows the heart rate down just a little bit. But it's really the SA node that is our pacemaker of the cell. Now, an EKG picks up on all of the electrical impulses in the heart, and it can provide data about heart health. Now, these have to be read by an expert that knows what they're looking for. Machines typically do it now, but again, it's in a lot of human error involved when you're dealing with EKG. The patient could move, the lead could be put in incorrectly. So there's a lot of things that can go wrong to give you a false reading. So someone needs to really look at it that knows what they're doing. So Sandra, is when a heart murmur, when one of the valves isn't closing all the way? Yes. That's usually what a heart murmur is. All right. Usually you can hear it as a swishing noise. All right. Heart murmurs are usually benign, which means they're not really a big deal. Like me, I have a slight problem with my valve on my mitral valve, and it opens just slightly. So you'll hear a little bit of a heart murmur, but it's not enough to where it affects me. All right. But some heart murmurs are serious, and you need someone that can listen and determine what those are. But usually it is one of those valves that's incompetent. It's allowing blood to flow backwards. All right. Now, a heart not pumping in a proper pattern or skipping a beat, that can be picked up on the EKG, and that would be a false, not a false reading, but an alarm reading on that. So when we look at EKG, you can tell how much, how fast the heart's beating, but you can also tell the pattern of electrical activity in the heart and whether it's skipping a beat or whether it's not beating correctly. All right, so again, our SA node is going to fire. That's going to send a signal to our atria to basically to contract, right? And then the AV node is going to delay that signal. And then we're going to move that signal down these bundle branches, and then they are going to move up the Purkinje fibers, which are these on the side, and it doesn't have those labeled on here, but that's what those are called. This is called the bundle of His here, and then these are the left and right bundle branches, and then the Purkinje fibers run up the sides of the ventricles. This is the wiring of the heart. So again, we're going to set the pace here with the SA node. It's going to delay a little bit at the AV node. Then we're going to send the signal down to the ventricles, and then that's cause the ventricles to contract. So when the atria are contracting up here, the ventricles are relaxing. When the ventricles are contracting, the atria are relaxing. All right, and that's that lub-dub sound that you hear with the heart. Is that boop, 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 that you hear is going to be from the signal sending impulses to the muscle to contract. All right. Now, if I have an SA node that's not working properly, I will have to get an electronic pacemaker. And some people have to wear these, and the newer ones, and I may be mistaken when I say this, but I'm pretty sure the new ones you can actually charge internally, kind of like you do with your phone when you lay it down on one of those pads and it charges without having to plug it up. I think that technology is there now. So they used to have to remove these and change the battery every so often, which was a pain. But now I think they can actually recharge them through the skin so that you don't have to do that anymore. But this is just going to send an electrical impulse to the heart to make it beat at a normal rate. All right. So again, some people have to wear these if their SA node is not working properly. All right. So a decrease in pH, I've been talking too long, causes the SA node to increase the heart rate. So this is going to benefit a person during strenuous exercise, because remember, when CO2 builds up in the blood, it causes the pH to drop. That's going to signal the heart to start beating faster, and that's going to get us more oxygen and, more importantly, CO2 out of the blood. All right, I'm going to stop here because I forgot I didn't put the EKG stuff in here, and I want to make sure I do that next time. So we'll start with EKG, and I'll run through it with you, what those little things mean on the graph, the QRS complex, the T wave and the P wave and all of that stuff, so you'll understand what that actually represents. Right? I think that's beneficial to know, because you may have heart issues one day where you have to look at one of those and see what's going on. So we'll start there, and then we'll get into some of the homeostatic imbalances like heart attack, heart disease, strokes, all of that. So I'll have some more stuff with you. I don't have a quiz today. I meant to make one yesterday, and I got so busy I wasn't able to do it. I was having to work on some microbiology stuff. For you guys in the lab, I have all of your lab papers ready to give back. I've got those graded. They're in the grade book. Again, we'll finish our dissections today and get those out of the way so we can start working on the human anatomy stuff and kind of catch back up with the class here. So if you don't have any questions, we're good to go for today. Don't forget, I moved your test out to the 31st, so you don't have to worry about that this week. Just make sure you keep up with your regular homework, and I'll try to catch us back up. Again, there's just a lot of material to cover in a short amount of time with this class. It's about 5 classes in one, really, if you look at it the way I look at it, because I'm teaching animals, plants, human anatomy. We'll get into ecology later. All those could be individual classes. But so anyway, that's it for today. So again, I'll make this recording available for you guys if you want to go back and look at some of this stuff. Don't forget those diagrams that I showed you earlier too.